Okay, so now I'm looking at the LRU cache problem. So the main problem of the LRU cache is that it is a data structure which is containing items in an order from in the order in which they were added in the queue. And the LRU cache is basically, firstly, we can discuss about a cache. So what is a cache? A cache is a memory which is easily accessible, which is relatively easily accessible compared to a normal database, wherein a database requires a lot of time to retrieve across a network. A cache provides a storage which is having low latency and which can store the most important items of data that we have and which are most frequently needed by any application. So, for example, a Chrome browser or any browser may have a cache mechanism where it stores the data that it retrieves with respect to the styles, with respect to the scripts that are needed frequently. And there are CDN servers which furnish some JavaScript or the jQuery, for example, a jQuery framework where a CDN acts as an edge server and it provides files which are ubiquitous to many sites. So if site A and site B are both using this particular file, then it does not need to be downloaded and reloaded every time a new site is being fetched. And in that case, the browser can just cache these kinds of files and quickly access them from their local storage. So in our case, a cache is having different kind of terminologies. So a cache hit is something where we find the data that we're looking for, so we don't need to then further query the database. A cache miss is exactly the opposite, where the data is not available in the cache and it needs to be further looked up in the database. The next thing would be stale data object in the cache, where the data has been updated in the database, but that uh, that version of the data in the cache is an older version, and hence it can't be used further. So when a stale data object is found, then that's something that needs to be dealt with through database calls. And yeah, I think those are the main terminologies that we have with cache. And so, yeah, the cache provides us a kind of a quick storage where we can directly use the items that we need. The eviction policy of a cache is something that is done when the cache is full and needs to accommodate more items. So we can evict certain items from the cache to make space. And the frequently used cache eviction policies are the LRU cache policy, where we remove the least recently used data item from the cache. Another would be the most frequently used cache, which eliminates the least frequently used items from the cache. So today we are looking at the LRU cache, where the eviction policy would be LRU. And the way that this can be handled in Python is either through a order dictionary, where the order dictionary is a built-in class, which is a hash map, which also maintains an order in itself, and it has functions such as move to end, which can help us in maintaining the most recently used items, which works in the order of space, order of one complexity. And it also maintains the last item that we have. So an order dictionary would be a kind of a built-in uh, library that we can use, a built-in class. And Another way of doing this would be using a double linked list along with a hash map, wherein the order is maintained through the hash map. I'm sorry, the order is maintained through the double linked list where we have a head and a tail, where the head would be from where we are inserting the items, and the tail would be where we are evicting the items, that is the least recently used items. And with each node of the double linked list, we are storing the reference of that node with the key of that node and the value being the reference in a hash map. So the aim of using a hash map is to directly index all the references of the double linked list so that we can perform operations in order of one time. So suppose there are standard operations that we need. Suppose we want to get a value from the uh, from the from the cache. So we can directly get the key from the user. The key has a reference stored in the hash map. That reference leads us to the node of the double linked list, and we can then remove that particular node and insert it at the end of I mean the head of the of the double linked list that represents uh, that particular node was the most recently used node. So that's how we maintain the most recently used. Along with that, we have the operation of adding items to the cache. So if a particular key is not found, we can just add it at the head of the cache, and the most recently used item becomes the new item. And if the length of the cache exceeds the capacity, that's when we use the left pointer to evict the tail element of the cache, and we remove the hash map entry of that particular element. So that gives us the basic operations in order of one time of insertion and deletion using both the double linked list and the hash map. So yeah, I think we can get started with the code. I have a basic template given to me, and these are the properties of the node that I was thinking about. Along with that, the hash map stores key and value, where the value is the reference of the corresponding node in the double linked list. Right. So I think that's about it about the description. We can begin this by initializing the node class. For here we have self dot key is equal to, so we'll define this in an init function. Self dot key is equal to key self dot val is equal to val. Along with this, we'll need left and right pointers as well. So we have this node, and suppose we have node 1 initially. Node 1 is connected to node 2 is connected to node 3. Along with this is connected to none. This is connected to none again. There would be a pointer from node 2 from node 1 as well. Similarly, a pointer from node 3 to node 2. So an LRU cache should initially have a dictionary, which we can call as what would be a good name for this dictionary? So this is the map that is connecting our cache. So we can just use a cache map name. Along with this, so the cache needs to have a head as well as a tail. And I think there should be some variable renaming that needs to happen over here. A node can have a next and a previous pointer, and we will use the left and the right pointer to denote the end and the I think we can use another naming convention. So we can use the head and the tail over here. So the head is equal to none, and the tail is equal to none. We evict from this end and we insert at this end. Along with this, I think we will need remove and insert functions for this LRU cache where we are removing and adding the elements at the end of the LRU cache, the building list. Okay. Along with this cache map, I think we need some association with the nodes that we have. So instead of just having null values over here, I'll initialize a node with 0 and 0. So that gives us dummy nodes for the head and the tail. Okay, so with the get function, I'm firstly assuming that we have two helper functions for our class where we are removing a particular key. Along with this, we are inserting a key and a value at the end of the LRU cache. Okay, so we can write these functions at a later stage. We can use some abstraction right now to assume that they both remove and insert the elements. Right. Now, if we need to check if the key is already present in the hash map, so if self dot key in self dot cache map, Then we need to update that particular value. So self dot cache map. I'm sorry. Over here we are returning the value. So it doesn't need to update anything. So we are just returning it. So yeah, return self dot cache map key. So this gives us the node that is present in the double linked list. And from there we need the value of that particular node. So this particular variable, not val. Else we are just returning a -1 as suggested over here. Now, once we have figured out how we need to return that particular value, we also need to place it at the end of our double linked list. So self dot remove from the link from the cache, the linked list. So let remove key and then self dot insert key, comma. So I think the value is already set for this node, so we don't need to actually. Yeah, I don't think we need a val parameter over here. Or do we need that? Let's think about it. When we are inserting a particular node, I think we need to set that particular value as well. So suppose we will be putting a new node at the end. In that case, we can initialize the value and we can initialize the value in the node itself and we can, yeah, just insert it using the key. So we don't need to include this val in the insert function parameters. So yeah, cool. So self.insert key, that makes it simple enough. Along with that, we need the put function. So in the put function, I can see we have the key and the value. So first we need to check if we have the particular key in the cache map that we have. Because if it's there, we just need to update it and repeat these operations to set it at the end of the cache map. So if key in self.cache map self dot remove cache map self dot insert self dot key self dot insert key. Before doing this, we should actually update the value. So self dot cache map of key dot value is equal to value. Now inserted it at the end. Mhm. If it's not present in the cache map, I think this operation is repeated in both cases, so we can just take it out of the if condition. And I need to think about this a bit. So if it's not present in the cache map, we need to actually create a node for this and then insert it at the end. So we can't just directly update it, right? So yeah, else we can create a node self dot cache map of key. is equal to node of key and val value. So that gives us the pointer. And then we insert this particular node at the end of the double linked list. So self dot insert key, and that's it. Yeah. So at the end of these operations, if we find out that the length of the current LRU cache is greater than the capacity, we need to actually evict the node. So I think I missed this thing over here. We haven't actually set the capacity variable of the class capacity. And now we check the length. If length of cache map is greater than capacity, this is a class variable, so self dot capacity. Now we need to remove an element. So self dot remove left, self dot next, self dot left, dot next. I think is it next? Self dot tail dot x tail dot right, tail dot right. So over here, the thing that's happening is that we are evicting the last node that is there. So the last node is held by the right pointer of the tail that we have. So we are just doing self dot tail dot right. We are removing that thing. And yeah, I think that should be it. We are not returning anything in this function. So yeah, I'm just looking at the function and doing a virtual dry run with some dummy elements. So suppose we have 2 comma 2 initially in this example. So 1 comma 1, we are initializing this, then we are getting, so we are putting this. So if case this condition is executed, the else condition cache map of 1 is equal to node, we are initializing a new node, key and value along with that, and then we are inserting the node at the end with the key. Capacity is still lesser than 2, that's fine. If we want to update the value 1 comma 2, so we remove that key, insert it at the end, and then we have the pointer over here, and we are just updating the val of that. Yeah, I think that should work. Now we need to work on this remove and the insert functions. So let's design a case for that. Suppose we want to remove the first node over here. There should be a pointer from here to here, gain from and to node 3. Suppose you want to remove node 2. Okay, so this pointer needs to be assigned to node 3. This pointer needs to be assigned to node 1. So we'll name this as previous, this as next, and we need to eliminate this. So we need to do a remove from the cache map for this. Right, so let's get this. We first get the node that we want to remove. So node to to be removed is equal to itself a cache map of key. Now the previous node is equal to node to be removed dot left. And the next node is equal to, so I can name this as nxt node to be removed and right. And now previous dot next previous dot right and nxt dot left need to be initialized as node to be removed and right and node dot left. So this bypasses the current node that we have. Next, we can just remove the node from the cell node cache map. We delete this. That is destroyed. For the insert, we need to, so suppose you want to insert a node between the last dummy node and node 3. So let's move these pointers. And yeah, so the previous node would be node 2. The next node will be the dummy right, the head node. So yeah, I think this is what I should do. Right. So over here, if we look at this, the previous is next pointer needs to be changed to the new node, and the dummy node's left pointer should be changed to point to the new node. And we need to add the entry in the cache map. So assuming this new node to be new node and it to be in between. So we need to update these. So firstly, we can create a new node. Or do we have a new node already? Let's check that out. Right. So over here we have assumed that we are creating that particular node and we are just inserting it over here. So we need to retrieve the value of the new node firstly from the map. So self dot cache map of key is equal to new node. And we need to set the left and the right pointers. So we know that we need to insert this at the head's left pointer. So head dot left would need to point at the previous node of new node. And firstly, we need to save these values, I think. So previous is next can be stored. Yeah, first I will define the previous nodes, previous and the next nodes. So head dot left is the previous node. Next node is head itself. Now we have the value stored. Then previous dot right is equal to new node. Previous next dot left is equal to new node. Then we initialize the left and right pointers of new node. New node dot left is equal to the previous node. New node dot right is equal to the next node. Let's look at these operations. If they are correct, we are getting the value of the linked list node firstly. We are initializing the previous and the next nodes as the heads next and as the head. Then we are doing the previous dot right and left. We are assigning the left and right pointers. And then we are initializing the new nodes left and right pointers. So yeah, I think this is correct. So as far as I'm thinking, these are all the implementations that we need. We'll insert, not needing to delete anything. Let remove deleting the particular entry. Let's see. Right, I think this should be self.head. Have I made a similar mistake somewhere else using tail? Right, we are getting this error where none type object has no attribute, right? In line 46. Okay, what is happening over here? Let's see. have the insert value, 1 comma 1, the put value. So with put is trying to insert the key. We're trying to insert it at the head. We are seeing that there's nothing in the left pointer of the previous. So the previous to right is actually none. Okay. I think I forgot to link the head and the tail at the beginning, and that's what is causing this issue. So both of them are not intertwined and they are linked in null spaces. So that's why they are not initially allowing us to insert it. So yeah, we can just initialize their left and right pointers to point to each other. So self dot head dot left is equal to self dot tail, self dot tail dot right is equal to self dot head. Cache map is not defined, so we got rid of that error line. Okay, this is self dot cache map. These are some trivial mistakes that I tend to make. Okay, now key error one. So this is happening in the line 45. So we are trying to insert a new node, and we're not finding the key of that node. So why is this happening? An insert function is called through which function? Through the get function. Line 57. So should I make operations on the dictionary on the cache map in the remove function or not? That is the question. Because I'm assuming that the insert only works on the double linked list that we have and on the double linked list, and the remove function in that case should also not work on the dictionary, such as removing items from the dictionary, and this can be done in the function that is calling the remove, I think. Because in this case, if we are removing that particular key, it is removing the key in the map as well inside the remove function over here. And it is then trying to insert it, and insert is assuming that we already have that particular key stored in the dictionary. So there can be two cases over here. We can either include the construction of the node in the insert function as well itself instead of doing this over here. I think that would make more sense because yeah, because the function should itself be inherent in both operations in the cache map as well as the double linked list. So let's try to use this over here. So we need to check that we are only inserting when we don't have it in the dictionary. So we are here removing it first and then we are inserting it. And then we are getting the value of it from that particular cache map. Is insert being used anywhere else? Yeah, we don't have that key in the cache map anymore. I mean, it's not present. It does not exist in the cache map. So I think this makes no sense. New node. You're first getting a new node. Yeah, then defining this entry inside the cache map as new node. It is more readable in this scenario. Let's see now. Okay, line 46 in the insert. Okay, so insert should have a value as well when it's, I think, and this might be a bit counterintuitive with what I've said before, but should we add a parameter in the insert function or should we, because then the value needs to be retrieved over here before transferring it over there. These are some design decisions that need to be made. They are very important, I think. We can define the removal of the dictionary outside the remove function and we only decide to work on the double linked list in the remove and the insert functions because I don't want to introduce more confusion with adding parameters which are not needed over here. So yeah. Mm, so we should have the creation of this node over here. We should insert that key. We are creating it over here. We should have the deletion. We don't need to delete that particular key over here, but we do need to delete, take this out of here. We need to delete it over here. This is self dot to, right. I think there would be some errors, but I think we can solve them quickly. The node is not defined. Yeah, I think I made some changes over here. This is already defined, so new node is equal to this. There is a key error over here in line 38. Remove assumes that we already have that particular node in the dictionary. And from where is this being called? From the put function. That function 974 tail dot right. Okay, let's try to debug this small issue. Yeah, I'm kind of thinking what's happening over here. I'm trying to get the flow of the problem because we don't know the exact point on at which operation the error is happening. But I think when it's trying to put a new value, that's when it's trying to, and when it's seeing that we need to remove the tail value, that's when it's facing this issue. So let's see, self.remove, self.tail.write. So tail.write should have the last value in it stored. Let's take this logic. There's a key error, so we can't find that particular key. Let's try to print that key. Is one. Let's try to see what the values of the cache map are. Yeah, so I think this needs to be simplified over here. This can just be next, and this can just be previous. I think I kind of get the bug over here now. So I am passing the pointer itself and not the key that needs to be used for the removal. So I'll just another variable self dot variable dot right is equal to this, and then we are passing the key of the LRU node. And that is the reason why we store the key as well in the nodes. Right, the same issue again, and we go. Key. So what do we need to return in those cases? No, no, no. Well, so we should ensure that this, so I should ensure that the LRU node is actually removing the keys. Is that happening? Let's see. So I just found this bug over here. I'm not returning the -1. I'm just writing it in the code editor. Right, so this is working now. Let's try submitting this finally. Yeah, all submissions passing. Right, so the mistakes that I made over here uh, were plenty, and let's kind of analyze the mistakes. So I firstly was updating both the dictionary as well as the double linked list in the remove and the insert functions, which was not actually needed. We have to handle them outside of them, and the insert and the remove only needs to focus on the double linked list because there were some issues that were happening with access of the keys when both the operations were working simultaneously. Uh, the next issue, the one of the most trivial issues was that I was not returning the -1 over here. Another minor naming convention issue might be that I was assigning both these variables but not using them in the next step. But that wasn't an issue. It was just an oversight on my end. Uh, the first issue that we had was I did not connect the head and the tail when the cache map is completely empty, and hence when the nodes were getting inserted initially, the left and the right pointers were pointing towards null. Hence, we were not able to add the new nodes. Yeah, I think those were the mistakes that I made, and yeah, by the end, I think conceptually it was clear that how do we implement the LRU cache. We just had to deal with some edge cases and some design issues along the way. But yeah, I think I passed it. Yeah, a good question to understand the design decisions that need to be made at while designing a complex data structure like an LRU cache. And I think this is a structure which is kind of tricky at the beginning, but if I try to do it again sometime, I think I'll be able to crack it pretty quickly the next time. So